Hello dear friends, welcome back to my channel. I'm Gerard and I'm here to study math together with you. And so we are still doing differentiation. So right now we are going to start with stationary points. Stationary points. Stationary points, what are these? We'll talk about them in a minute. But the last time what we did increasing and decreasing functions. So if you watch my last videos, my very previous videos, so you know that when if we have a function x and we have the derivative, and if the derivative is positive, greater than 0, exclusively positive, then it is an increasing function. So we say it's an increasing function f. But if it's negative, strictly negative, then it is a decreasing function. So we have understood those things the last time. So now we are moving on with stationary points. So we have a function, for example, y is equal to x squared, and this is the curve of it. What we know is that here, if we want to find the dy by dx, the derivative, we'll have 2x. So 2x should looks like this. We know that this is y is equal to x. So it should be a line like this. So the last time I said that the range for the function this is positive from x less than 0 and x greater than 0. It's only when it's at x is equal to 0 that it's 0. But that's not true. That's not true. It's for the derivative. If the derivative is equal to x squared, then this is true. But if we want to find the derivative of x squared, y is equal to x squared, we have 2x, and it's just a line like this. Just a line like this. So here is a function fx, and here the line is f prime, the derivative. Okay, just for you to know, then the range for which the function is increasing is when x is greater than 0. So this is not good. Okay, alright, so I hope that this is clearer now, but the rest was good. Just I got this and this confused. Alright, so let's look at the stationary points. Stationary points. Stationary points is so stationary points are when the derivative f prime x is 0. So for example, here it's 0, it's decreasing, increasing. So that's how it is. And so let's stay with fx is equal to x squared. We know that the prime x, or the derivative is 2x. But if we define this, so it exists. So for the range of x is an element of real number, yeah, consider as a real number. So this can be a definition for all the real numbers on this line, natural, or for all the integers, if you want, integers, we have a value for the function. So this is not the definition. I think this is the value, Abgabels in Latvian they say, but the definition is something else. So depending on this, on the definition of the function, so if we say that for y greater or is equal to 0, so this is the definition, we are not going to go down, then we will only have this positive. But here, when the derivative is negative, so we don't, so I don't know, we can say that. I think now I'm overthinking it a little bit, because clearly the gradient is decreasing here and then increasing if we look at the function itself. So this is how it looks. It's negative and then positive. Alright, but where really it is at 0, so this is a turning point. Turning point means that it goes from negative to positive. This is a turning point. So you have 3 types of turning points or stationary points. You have this, or this, or you have this, or you have let's say this. No, this is a little bit weird. Let's say yeah, we have something like that. We have something like this. We have something like that. So here we have a maxima, and here is a maximum. Maxima, we call it a maxima. So we have a maximum point. Here we have a minima, and here we have what we call a point of inflection. Inflection, point of inflection. I was thinking that inflection will be written like this. It looks like French version here. Okay, so any point on a curve where dy by dx is equal to 0 is called a stationary point. At a stationary point, the gradient of the curve and the gradient of the tangent is 0. So if we draw a tangent here, for example, a tangent here, so it's going to be 0 and horizontal. At a stationary point, the gradient, there are 3 types of stationary points: minimum point, maximum point, and point of inflection. Questions involving points of inflection have not been included in this chapter, and they will not be sent in Cambridge International blah 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 blah. That's from a book that I'm using as a reference and as a guide to revise. So right now inflection is just when it's changing, but it can also, if I'm not mistaken, it can also be like that. You know, like it's decreasing and again it's decreasing and increasing. A decreasing acceleration, an increasing acceleration, a decreasing deceleration, and an increasing deceleration. So these are terms that might be used, you know, in physics, for example. So again, what is the range for which this function y is equal to x squared is positive? We differentiate to x. 2x is like this, and its square is positive, so x is greater than 0. That's the right answer. I got a little bit confused by this, but hopefully you will remember this. Find the coordinates of the stationary points of the curve y is equal to 6x minus 2x to the power of 3. So this is quadratic equation to x to the power of 3, and it's negative here. So what do we do then? We have to differentiate it, yeah, because we're looking for the coordinates of the stationary points of the curve. So at which point dy by dx is equal to 0. So we know that it's 6 minus 6x to the power. So we have this. We can also put 6 outside. We have 1 minus x to the power of 2. And dy by dx is equal to 0 when since this is just a factor, we can equate this to 0, and we divide by 6. We have 1x2 is equal to 0 minus x is equal to minus 1. We divide, or we multiply by minus 1 on both sides, we get this, and root square is plus or minus 1. This I take off. Alright, so we have come to this conclusion. Yeah, you have to come to this conclusion that the derivative, this, is going to be sketched in just a moment. I will sketch it. So I can erase this because we know that it's plus 1 and minus 1. So we have this, we have minus 1, 1. And since it's negative, we know that it's going to be an n with a maxima. So I would say it's like that. And if I want to find the line of symmetry, it's also possible. Since it's 1 and 1, so it should be symmetric here on this line, the x, the y. I can try to make a better sketch, probably. So let's do this. We have 1 minus 1, 1, and if we sketch it, it should be symmetry on the y-axis. This is the x-axis. Y-axis, I wanted to write axis here. Okay, so guys, what are we asked? So determine the coordinate. Find the coordinates here. So we need to know this. So this is the point where the y by dx is equal to 0. We know that it's a maxima, and we can take any point here, For example, we can take I don't know, half. So if we take half, 6 minus 6 multiplied by 0.5 to the square. So quickly use my calculator. Half to the square times 6 is equal to 1.5, and this is negative plus 6. So I have 4.5, but it's going to be negative again because this is minus 1.5. So the gradient is negative here, and then it's going to be positive. If we take, for example, 1.5 square, yes, times 6, what's this? It's not 1.5, it's 0.5 square times 6, and then it's minus, and then we plus 6 with it, 4.5. So we have 4.5 here is positive. So you can also make a table for it. You can put values of x here, values of the y by the x here. So you have many values, for example, minus 2, 1, minus 1, 0, 1, 2, and so on. So you will see that it's going to be, it's going to change. So when x is equal to minus 2, for example, you have 4 times minus 6, it's minus 12. 4 times minus 6, it's minus 24, sorry, minus 24 plus 6 is going to be minus 18, so it's negative. At point minus 1, it's going to be like that, and then it's going to start to increase, because if you take at 0, it's actually 0, it's 6, the derivative is 6. Yeah, the derivative is 6. If we put 0 here, we get 6. So we have sketched now the derivative. This is not the function. The function is with power cube. So at 0 it increases, and then at 1, so it's going to be 0 again, and then at 2 it's going to be so we see it's 0 here, don't we? We see. Then if we have value this, so it goes down, 0, up, down, up, down, up. It should go, no, up, down, up, flat, and down. Should go down. Let's see if it's negative. So 2 is 4 times 6 minus 6. It's minus 12. So minus 12 plus 6, it's minus 6. So this is the table that we have here, and it means that we have two turning points. We have two turning points. We have a turning point here and here. Here. I will switch back to pink. We have two turning points. So if we have to plot the graph, it's going to be something like this, this, and this. So this is this function. So at what point we have the turning points is at this point and this point. These are the coordinates. So how do we get this? So we know -1, -1. So it's very easy. We erase this. I'm getting tired. Erase this. We can insert this when it's -1 here. 2 -1 cube. This is going to be -1. -1 times this plus 2 -6. It's going to be -4. So we have the coordinates -1, -4, right? That's one coordinate here, here, -1, -4. And if we want to find this coordinate for this point here, here we have a minima, here we have a maxima. So we just replace 1 in this, and probably we'll have 4 here. So what do we understand from this? We understand that we got the coordinates. That was what was asked from us. And the second part is sketch the curve. We have done it in pink. The first one in green, that's the derivative. So that's it. That was about turning points. So how to sketch things, and just have to put some values in this. And so I think I might be able to do another example for this, just for the sake of clarity. If we have a curve which is 2 divided by 2x plus 1 minus 1 plus x. So find the coordinates of the stationary points of the curve and determine their nature. Exactly what we did before. So here, this looks awful. This looks really awful. Look how complicated it looks. But if we rewrite this to x minus 1 to the power of minus 1 plus x, well, something like that. Well, actually, what can we do? We can put both on the same denominator. 2x minus 1 plus x times 2x minus 1. So we'll have 2 plus 2x squared minus x. Yeah, that's a quadratic equation divided by 2x minus 1. This looks like a quotient case for me, quotient rule case to differentiate, you know. It looks like a quotient rule case for me. But what can we do? What can we do? So I'm looking at the book right now. To differentiate such a thing, you need to know uh, the quotient rule, which is gx time fx prime, I think. Gx time fx prime u there is v times du times dx, and so on and so on. So this is a whole formula. We haven't done such thing yet, but what we have done is substitution. So what can we do here? So I have done some research after pausing the video. This original function is much simpler than this. What does that tell us? That tells us that we are now getting in troubles with the quotient rule, which will probably be more time consuming to do. So there is another way. There is always another way to do the differentiation, or to find the derivative of this function. So for that reason, and because I didn't make any video yet about quotient rule, and if you're using these videos or materials to learn, so it's not going to be fair. So I'm going to uh, show you how to do it without quotient rule, which is actually smarter because we are not complicating things. So I will rewrite the function. This is 2 over 2x minus 1 plus x. So what we can do here, we can do a substitution of this. Okay, so this we know how to differentiate, but to differentiate this, we can say let u is equal to 2x minus 1. So which will give us, if we go, I would say, if we go by terms, differentiating by terms, yes, or we say chain rule, we can say chain rule also, because that's what we're going to do. So we will have u here. So we have u here. Okay, so so du by dx is going to give you 2. Okay, so that's as simple as that. So let a is equal to 2 over u. So that's what I got here. Yeah, and you can rewrite it as 2u on the top. It's the same thing, and dA by du is going to be minus 2, like that. This is a differentiation, and therefore you have now the possibility to have dA by dx. So we have du by dx time dA by dx, du by dx, no, was it du by dx, yes, time dA by du, sorry. So this will cut, we'll have dA by dx. So it might seem very complicated, but it's going to avoid us a lot of troubles for now. Once we will be comfortable with the quotient rule, we don't care, we can solve a lot of things. But substitution might be also a very easy way to do things. Very easy way to do things. So to get, you always have to use, you know, your brain. Um, so we say u is equal to 2x plus 1. Remember, the u by the x was 2. I erase it. The u by the x was 2. So 2 times dA by dx, dA by du is minus 2 over u squared, which gives us minus 4 over u squared. And we know a square, we know what is u. U is this, just under it. So we should replace this here. So we have dA by dx, dA by dx. All right, and now what should we look for? We should look for dy by dy by dx. So dy by dx is going to be, let's rewrite this. All this I can take away. What we did is just very simple, very simple. I can, if you're having a hard time following me, I'm just going to redo it for you, because I did it once, and second time, of course, it's going to be easier. So we have y is equal to this. Y is equal to everything on the right of the sign equal to, but let's say a is equal to 2x minus 1. So we just broke this in two. We can say b is equal to x. So we have now two equations in this. We want to solve this, and we want to solve this term by term. And in this one, because it's down here, we actually could do just like, wait a second, I have done such a thing before. So if I have to do dA by dx, how do I do this? I just say 2 here, 2x minus 1 minus 2 times 2 is equal to minus 4, 2x minus 1 minus 2 to the power of minus 2. That's exactly what we got there. So you see, this is differentiated. I have just differentiated this. It's not that difficult. If we want to differentiate the a db sorry by the x, it's going to be 1. So since we have differentiated this and differentiate this, we can just add this to this, and a plus b is going to be y. So how can I write this mathematically? I will erase this. Just have to put yeah. I will erase this. Take something to write. dy by dx is equal to y is equal to a plus b. Yes. So if I want to differentiate this, I have to differentiate like dy by I don't know, like dy by this. There are two unknown. So it's just easier to say that y is equal to this if but this is what we got. yeah, plus 1. That should be the answer. Plus 1. Yeah, there's a sign, minus sign here. That's actually the answer. That's actually the answer here. Because I just differentiated a, so dy by dx, I will write it here to understand. So you see now you can use this. Substitution is very important, very, very important. Dy by dx is dA by dx plus dB by dx, because y is equal to a plus b. Alright? So if we differentiate this and we differentiate this, we are differentiating everything. This should be correct because the answer is the same. Alright, so now let's do the second part. It's very important because if you put the, let's say if you put this, 2 over 2x minus 1 plus x times 2x minus 1, and you expand this, and then you have a quotient differentiation like I did in the first instance. So you know that dy by dx is going to be like gx times f prime x divide minus fx times gx divided by gx to the square. So this is a long process. This is a very long process. Just break it in two, do this and that, you get this, you get the derivative, and after that you carry on. Well, I hope that I'll also use this. Substitution is very helpful, save you a lot of time, and the more you're calculating, the more you are able to make mistakes. So that's something to consider. Alright, so we got the derivative, and what are we looking for? We're looking for the coordinates of the stationary points. So we don't know how many stationary points we have for this. I'm thinking that we have maybe 1 or 2. Hopefully only 1 or 2. So what we need to know is when this is equal to 0, what do we have? We have minus 4, 2x minus 1 to the power of 2 plus 1 is equal to 0. So what happens here, we have 4 over 2x minus 1 to the square, and minus 1 minus here. We multiply by minus 1 on both sides. We have this. And now if we will multiply by this on both sides, we will get something very interesting. Very, very interesting. So we'll get 4 is equal to 2x minus 1 to the power of 2. And this is mathematically correct. And we can expand this now because we don't have to deal with differentiation anymore. So this is going to be like this, and then using what we know, we have 2 times 2x times minus 1, and then we have plus this to the power of 2, which gives us 4x squared minus 4x plus 1. So we have this is equal to 4. And if we bring this on the other side, it will make things much simpler. So we have 4x squared minus 4x plus 1 minus 4 is equal to 0. So we'll get 4x squared minus 4x minus 3 is equal to 0. So we have come to something that is very simple to us, and since we want to find the roots, we are going to put 4 outside. We have x minus x squared minus that, divided by 4 to 0. So this is just a factor. We can just divide by 4 on both sides. We'll get rid of it. And so we just got rid of it. This is fantastic. So we are left with this x2 minus. So how do you think we'll solve this, knowing that we have worked with quadratic equations and so on? So to find the roots of this, we better use this b squared minus 4ac divided by 2a. We just use a formula. We're not going to try to factorize this. Yeah. So I'm going to do it. So let's write here a is equal to 1, b is equal to minus 1, and c is equal to so I have a lot of minus here, thinking if I will multiply by minus on both sides, we'll get minus 1 here, plus, and then plus 3. I think it's possible also. So then minus, I will get minus 1 plus or minus, and then I get b squared is 1 minus 4, 1, and 3 over 4 divided by 2a. 2a is minus 1. So we're getting there, guys. We are getting there, guys. Oops, I need to erase here. So let's do this. Minus 1 plus or minus root 1 minus, it's going to be plus. So here we see that's wonderful. We get 3. We get 3 divided by minus 2. Wonderful. And this is 4 because we have a minus here, so we have 4. We can rewrite this by 4 minus 1 plus 2 divided by minus 2, or we have minus 1 plus, no, minus 2 this time, divided by minus 2. So this one will get you to let me do it clearly, because this is something very long. So I have 1, this is 1 root, and the other one is minus 3 over minus 2 is positive. So that's what we got. We got 2 values of x, and we can easily now find the coordinates for the turning point. We just remember that we had y is equal to what? I wonder if I can use, no, let's just use this, 2x minus 1 plus x. So if we have x is equal to minus half, it's going to be 2 times minus half minus 1. This is going to be minus 1, minus 1, minus 1, minus 2. The 2 divided by minus 2 is equal to minus 1. So minus 1, yeah. And that was just for this part. Wait, let me redo this. Let me redo this. So we have 2 divided by to minus half here, minus 1, plus half here, plus minus half here. So we have, what do we have? This is going to be minus 1, it's minus 2. 2 divided by minus 2 is minus 1, minus half. It gives you minus 3 over 2. So minus 3 over 2 is a correct answer for y coordinate. And let's quickly do the other one. So once again we have y is equal to 2x minus 1 plus x, and if we put this here we have 3 by 2 minus 1 plus 3 divided by 2. So here we have 3 minus 1 is 2, we get 1 plus 3 over 2. We have 5 over 2. Yes, we have 5 over 2. This is the second coordinate. The first coordinate, the second coordinate of stationary points. And so now we don't know what kind of turning points they are. So we still have to find what kind of turning points they are. So guys, so what we know is that we have a function, which I wrote, y is equal to 2 over 2x minus 1 plus x. We know that f prime is something that we calculated. So we need to know how h prime is changing after and before these points. So we have x here. You can make a table here. X. I can use this just to wake up a little bit things. So I have x, and then I have dy by dx, and I can throw a lot of values here. For example, minus 1, minus half, and then 0, and then 3, 2, and then I can just put something like 2 here, anything. So I will get values, and just to make this video shorter because it's almost like 1 hour now. So here we will have something positive, we have 0 of course, here we will have 0 of course, but here we have negative, and then we have positive. So which means that if we have something like that, this is a maximum. So this is a maximum, maxima, and here, because we have this, so this is a minima. This is a minima. So now if we have to draw the curve, we know this, we know what's the maxima, what's the minima, and you know, if we have to draw something, this is y, this is x, we have points like minus half and 3 divided by 2, right? So the equation itself, we don't really know. We know that something happened here. This is maxima. Maxima is like this. So like this, and then is the maxima. And then what happens here? And then I have a minima here. Minima here. What about something like that? You know, I think I think no, it can be because looks like there is another turning point here. This is a maxima. Maxima is here. Mm, can it be like that? No. When it's zero, what happens when it's zero? When it's zero, 2 divided by zero, 0 by zero. No, it's 2. It's 2. When x is 0, it's 2. Wonder how to plot this. But if you want to plot this, you can also just throw some values of x, obtain the value of y, plot the points like that, like that, and like that, and so on. But that was an interesting, very interesting thing to do. I think this is maxima. Yeah, we are trying to plot the function here, but this might be wrong because we want to have the derivative. Okay, so enough of this. I think we got the maxima, we got the minima, yeah, from the derivative, and so at these points they are zero. So this point they are zero. So this might just be the derivative. Ah, okay. What about this? This is this is what we talk about. We got this. Why not? Something like this. Yeah, something like this. If we will, hmm, and this is not on the x-axis. Y is not zero. It's negative something. So it should be like this, and then so this one is positive, and here it's also positive. So which means that it's here, has a minima here. It goes like that. The maximum. I don't know if it's something like that. This is a minima. This is a maxima. Guys, this is interesting. I think this sounds more plausible. I think that's more plausible. Alright, so thank you for watching and cheers. Bye.